So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna generalizing these two crazy integrals. And let me tell you a little bit about the first integral. This is the generalization of the Dirichlet integral actually. If you know about that, and you know what, basically the Dirichlet integral is, let me tell you about that. Dirichlet integral, and I one of my older videos, like I took almost 42 minutes to solve this integral. Sine of x dx integral from 0 to infinity is pi over 2. So basically today, this video is gonna be amazing, obviously, because we are just going to generalize that integral, and even we'll play around with the cosine way as well. So let's just talk about this. So proof. Basically, we are just gonna begin our journey from gamma function. Let's talk about gamma of c, right? Or let's talk about gamma of p, because I have used some p's here, so let's just talk about gamma of p, right? So we know that gamma of p is the integral from 0 to infinity of t to the p minus 1 e to the negative t dt. So this is the gamma function, and I have talked about this. I have made an introductory video on this as well, so if you want, you can check that out as well, right? And I would request you to just watch that video, because in that video I have proved this to p minus 1 factorial, but we don't need to talk about this in this video. Okay, so we have this thing, and now let's just replace p with 1 minus p here. So gamma of 1 minus p is gonna be integral from 0 to infinity. It's gonna be t to the minus p e to the minus t dt, right? Okay, and now our next step is let t equals ax. Okay, so basically gamma of 1 minus p is gonna be integral from 0 to infinity, and if we talk about dt, so that's gonna be a dx, and limits ain't gonna bother us, because when you plug t equals 0, x equals 0, and when you plug t equals infinity, x is also infinity. So it's ax to the minus p, and e to the minus t is ax, and we are, don't forget the a dx. Actually, I just forgot the factor of a actually over there, but it's all right. It's gamma of 1 minus p equals integral from 0 to infinity. It's a to the minus p, x to the minus p, e to the minus ax, a dx, right? Okay, so now since p and a are constants with respect to x, if we talk about, so that's gonna be a to the 1 minus p, x to the minus p, e to the minus ax dx. So that's gonna be gamma of 1 minus p equals a to the 1 minus p times integral from 0 to infinity of x to the minus p e to the minus ax dx. And now let's talk about, let's just write this constant in terms of an imaginary number. Let's say a equals ib, and we know that I is e to the I pi over 2. Yeah, we know that from the Euler's formula actually. So gamma of 1 minus p is gonna be, well, this can be written as b e to the I pi over 2 whole to the 1 minus p, 1 minus p, and times integral from 0 to infinity of x to the minus p and e to the minus ibx dx. Like this form I have used over here, and this one I have used over here actually. So this can also be written as gamma of 1 minus p equals b to the 1 minus p and e to the minus I 1 minus p pi over 2, right? And times integral from 0 to infinity, and it's e to the minus ibx over x to the p dx. And let me just multiply, wait a second, we can write this as e to the negative I p minus 1 pi over 2. Oh, I think I just messed up. Oh, there is no negative in front. I'm sorry about that. So I have to fix this again. So basically I have to plug a negative, and I can just write that down over here. So basically it's e to the negative I 1 minus p pi over 2 gamma of 1 minus p equals b to the 1 minus p and times integral from 0 to infinity e to the minus I bx over x to the p dx. And yeah, so this is what we are having so far. And now let me just remind you that we know that e to the iz is cosine of z plus I sine z, and I have proved this crazy. This is known as Euler's formula, and I have proved this crazy relation a couple of times, so you can consider watching that as well. So basically let's just replace z with 1 minus p pi over 2. So that's gonna be e to the, I'm sorry, let's introduce negative as well in front. So it's negative, so it's negative I 1 minus p pi over 2 is gonna be cosine of negative 1 minus p pi over 2 plus I sine of negative 1 minus p pi over 2. And we know that like cosine of negative theta is cosine of theta because it's even function, and sine of negative theta is minus sine theta. So let's just introduce. So basically this is gonna be cosine of this argument without any negative in front, and this is gonna be negative here actually. So let's just write that down. So it's e to the negative I 1 minus p pi over 2, and it's cosine of pi over 2 minus p pi over 2 and minus I sine of pi over 2 minus p pi over 2. And again we know that cosine of pi over 2 minus theta is sine theta, and vice versa with this sine one. So sine of pi minus 2 pi by 2 theta, I'm sorry, pi over 2 minus theta is cosine of theta. So we can replace this one as sine of p pi over 2 and this one as cosine of p pi over 2 from these two identities actually. So finally we are having e to the minus I 1 minus p whole times pi over 2. It's sine of p pi over 2 minus I times cosine of p pi over 2. So yeah, this is what we are having. And if we talk about the same formula, so if we replace z with minus b actually, or let's say minus bx, so it's minus bx actually. So it's gonna be e to the minus I bx, and it's gonna be, I'm sorry, cosine of it's gonna be minus bx and plus I sine of minus bx. So again it's e to the minus I bx is cosine of bx minus I sine of bx. And yeah, now we are just gonna replace these two things that we have got here. So this one would be replaced with this result that we have got, and this e to the minus I bx would be replaced with this one. Isn't that amazing? So basically on the left hand side we would be having what we are having, sine of p pi over 2 minus I cosine of p pi over 2 and whole times gamma of 1 minus p equals b to the 1 minus p integral from 0 to infinity, and it's cosine of bx minus I sine of bx over x to the p, and we are having dx. Now okay, so now for Dirichlet generalization, Dirichlet integral generalization, we have to take the imaginary part of this integral generalize. We have to take the imaginary part general. Wait a second, let me just write that down. We have to take the imaginary part of this equation actually. So taking the imaginary part, so imaginary part of sine of p pi over 2 minus I cosine of p pi over 2 and gamma of 1 minus p equals imaginary part of this integral actually b to the 1 minus p integral from 0 to infinity of cosine of bx minus I sine of bx over x to the p dx. So if we talk about the imaginary part, so on the left hand side we would be having cosine of p pi over 2 times gamma of 1 minus p, and on the right hand side we would be having b to the 1 minus p times the integral of sine of bx over x to the p, and negative we would be get rid of that. So on the left hand side we are having cosine of p pi over 2 gamma of 1 minus p equals b to the 1 minus p times integral from 0 to infinity of sine of bx over x to the p dx, and dividing both sides with b to the 1 minus p, so that's gonna give us integral from 0 to infinity of sine of bx over x to the p dx. That's gonna give us cosine of p pi over 2 gamma of 1 minus p over b to the 1 minus p. Now using Euler's reflection formula actually. So why am I using that? Wait a second, let me just tell you. That's amazing. So we know that Euler's reflection formula, even I have proved this one as well, so you can just watch that as well. So it's sine pi z, and if we talk about isolating gamma of 1 minus z, so it's pi over gamma of z times sine pi z. So here we are having gamma of 1 minus p, so that can also be written as pi over integral from 0 to infinity of sine of bx over x to the p dx is coming out to be cosine of p pi over 2 and times we can write that as pi over gamma of z sine of pi z, and we had b to the 1 minus p as well. Now let's do some more simplifications here. We can write sine pi z as 2 cosine pi z over 2. Oh, I think I should have it's pi p, and it's gamma of z actually. I'm sorry, gamma of p. Yeah, it's good. So yeah, and it's sine of pi z over 2, right? So we can write this as 2 times of cosine of pi p over 2 sine times sine of pi p over 2. So let's just write that down. So integral from 0 to infinity sine of bx over x to the p dx equals, it's b to the p minus 1 times pi over gamma of p, and we are having cosine of p pi over 2 as well, don't forget about that. It's 2 cosine of p pi over 2 sine of p pi over 2, and hence we just got rid of cosine terms. And finally here comes the final result of this crazy generalization. Integral from 0 to infinity of sine of bx over x to the p dx is b to the p minus 1 times pi over 2 times gamma of p sine of p pi over 2. So isn't that amazing, guys, the way we just did that? Okay, we have also we are having another thing to prove actually. Don't forget about that actually. I'm so sorry about that. So it's the another integral actually, and you know what, we have reached up to here. Wait a second. Yeah, we have reached up to this equation, and we took the imaginary part actually, And if we talk about the real part, so that's gonna give us this result actually, so that we wanted for the second integral. So this equation is really important, obviously, because from that equation only we just got both of these crazy results. So taking real part actually, so if you talk about real part, so it's gonna be sine of p pi over 2 and times gamma of 1 minus p equals b to the 1 minus p integral from 0 to infinity of cosine of bx over x to the p dx. And finally, if we divide both sides with b to the 1 minus p, so it's gonna be cosine of bx over x to the p dx, and it's gamma of 1 minus p sine of p pi over 2 over b to the 1 minus p. And I think we shouldn't be stopping right here. We can do something better as well. So what we can do in that? Well, I'm just gonna use the reflection formula, which consists of cosine term. Like we know that. Well, I haven't proved it yet, but yeah, it's gonna be just take 3 minutes, and that's gonna be my next video actually. And I'm just going to use that in this video. So it's gamma of 1 over 2 plus z times gamma of 1 over 2 minus z is pi over cosine of pi z, right? So it's pretty easy actually, right? It's definitely easy to prove. And we are having some sort of 1 minus p here, so we can write that as 1 over, like we can write that as 1 over 2, like it can also be written as, wait a second, 1 over 2, and it's minus c, so it's 1 minus, we can write that as 1 minus 1 over 2 and minus p actually, or maybe we can write that as 1 minus 1 over 2 plus p. Yeah, we can write that, and that's gonna be our argument actually. So basically this gamma of 1 minus p can also be written as gamma of 1 over 2 minus, maybe we can write that as, wait a second, I think it's enough guys, and it's true actually, but we can just solve this further as well, but it's not gonna help us out. That's fine, and this is the final result actually that we have to prove. We had to prove. Just let's just take a look, and here it is actually. So yeah, it's not necessary to just go further without any meaning, but yeah, you can just go further. But I think I'm just gonna bring the proof of that with the thing that I have written over here, and then we'll talk about that. So yeah guys, we have proved these two crazy integrals, and I hope you got to learn something out of it. And if you got to learn something out of it, please make sure to like, subscribe and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. I'll be there to reply to your questions. Thank you so much, and love you guys. Just learn mathematics as I just explained you in the last video of mine as well. Goodbye guys.